Today, we are digging into the hidden science that, quite literally, builds the world around us. We're talking about the insane precision that goes into every skyscraper, every bridge, every tunnel you've ever seen. So let's get into it and uncover this hidden language that shapes our entire world. So, our whole journey today is about this incredible transformation. How do we get from a simple drawing, a blueprint, to a massive, real-world piece of infrastructure? It's a process that demands a level of accuracy that is, frankly, mind-boggling. It's a science that works silently in the background of every single construction project. I mean, stop and really think about that for a second. How on earth do you start digging a tunnel from two different sides of a mountain and have it meet perfectly in the middle? Or how do you lay the foundations for a massive bridge in the exact right spot, down to the millimeter? The scale is just immense, and there is absolutely zero room for error.
Well, the answer is a field called engineering surveying. It is the absolute first step, the fundamental discipline of measurement and mapping that makes all of this possible. You can think of it as the language that translates an architect's dream into a set of instructions that builders can actually execute on the ground.
Okay, so where does it all begin? Well, long before a single shovel hits the dirt, you have to create a perfect map of the area. And no, this is not like the map on your phone. This is a highly detailed, mathematically perfect model of the project site. And the foundation of that map is something we've all heard of, the geographic coordinate system. Latitude and longitude. Surveyors use this global grid to give every single point on a project site a unique, unchangeable address. It's the absolute starting point for every single measurement that follows. Now, what's really cool is how they use that system on the ground. They create what's called a traverse. They physically go out and establish this network of control points, like you see here, points A, B, C, and D, each with a super precisely measured coordinate. Honestly, it's like a high-stakes game of connect the dots that ends up forming the rigid skeleton for the entire project. And this is where the magic really happens. Once you have that traverse, you can plug those coordinates, those X and Y values for each point's position, into formulas to figure out all sorts of critical information. For instance, with just those coordinates, you can calculate the exact area of a piece of land with complete mathematical certainty. Okay, so we've got our map, we know where things are, but the real world isn't flat, and we don't always travel in straight lines. So the next big challenge is designing routes for things like roads and railways that can gracefully handle the natural landscape. Right, you just can't have sharp 90-degree turns on a highway. It would be a disaster. The aha moment here is realizing that every single curve you've ever driven on is meticulously engineered for safety. Its exact radius is calculated based on the speed limit, making sure your car can handle it smoothly. This whole area is a huge part of something called route surveying. And really, there are two main types you're dealing with. You've got your horizontal curves. Those are the ones you see on a map, bending left or right to get you around something. Then you have vertical curves, which manage the change in slope or grade. They're what create that smooth transition as you go up and down hills, making the drive safe and comfortable. Engineers have this whole toolbox of curve types to choose from. The most basic is just a simple curve, a single arc. But they can get more complex, combining curves to create a compound curve for tricky turns, or even a reverse S-curve when the terrain really throws them a curveball. Now, for centuries, this was all done with physical chains, compasses, and just an incredible amount of manual calculation. But today, today technology has completely turned this field on its head, giving surveyors an unbelievable new toolkit. Today's surveyors are armed with an array of what are called geospatial technologies. We're talking about super high-precision GPS, remote sensing from satellites, powerful mapping software called GIS, and photogrammetry, which is basically the science of making measurements from photos, often taken by drones. Remote sensing is especially wild when you break it down. Basically, a sensor, maybe on a satellite or a plane, records energy, like sunlight, that has bounced off the Earth. That raw data then gets transmitted, processed, and analyzed to reveal incredible details about the landscape without anyone ever having to set foot there. And drones have really brought this power down to the individual project level. A drone can fly over a construction site, snap hundreds of geotagged pictures, and software can then stitch all of that together into an incredibly precise 3D model or a 2D map. And it does it in a fraction of the time it used to take.
It's a total game changer.
So, let's put it all together. We've got our mapping principles, our route design methods, and our high-tech tools. Let's see how this all comes together in some of the most challenging and specialized engineering projects imaginable.
And the applications are just everywhere you look. Every single building has to be set out, which means its corners are marked on the ground with millimeter accuracy. You need that same precision for bridges, for sewer lines, and especially for incredibly complex projects like tunnels and canals.
Yeah, let's go back to that tunnel example because it's one of the ultimate tests of precision. Tunnel surveying is all about making sure those two crews, digging from opposite ends, meet perfectly. They use techniques like traversing and even gyroscopes to keep their direction true deep underground. It's a job that just demands absolute, unwavering accuracy.
Now, for something like a canal, the challenge is different, but it's just as critical. Here, surveyors have to create a super detailed profile of the route's elevation. Why? Because the whole design relies on gravity to make the water flow. If you mess up the vertical survey, the water might just sit there, or worse, flow the wrong way.
And that right there is the main takeaway. Engineering surveying is the crucial bridge between the world of design and the world of construction. It gives you the data, the framework, and the control you need to build incredible things with total confidence and precision.
You know, this quote from a surveying textbook really just nails it. At its very heart, it is all about one thing: making a map that accurately shows how things relate to each other in the real world so that we can then build new things and add them to that map.
It really makes you wonder, doesn't it? As all of our tools, from drones to satellites to GIS, get even more precise, even more powerful, what new feats of engineering are going to become possible? What's the next generation of surveyors going to help us build?